This is a little movie I made to help my physics students on account of the fact that we lost a whole bunch of class time due to Hurricane Sandy. The intention of the movie is to review how we built up our uniform acceleration model with the objectives that when we come back to school, we can pick up right where we left off. Students may recall that our first experience with acceleration was a lab we did in the MPAC, where student lab groups took balls and rolled them down aisles and worked together to produce data for position and time of the moving balls. Using their data, most groups produced a graph of position versus time for the balls that had a curved parabolic shape like this. Students took that data, squared the values for time, and replotted a graph of position versus time squared. And most groups got a straight line that looked like this. Next, we went back to our curved xt graph, and I showed the students how to take the slopes of tangent lines at various points on the graph. A tangent line is a line that intersects the graph at only one point. And I argued that the slope of the tangent line is what we call the instantaneous velocity at that point. That is, the velocity that the object is moving right at that instant. The students used a software program to find the slopes of various tangents to the xt graph. And they put those slopes in a little table. The table had the time of the individual point and the slope of that tangent at that point, which is the velocity. When they graphed the values in that table, they got a velocity versus time graph, which in most cases had a straight line that looked like this. Then we introduced a definition. We defined the word acceleration as meaning the change of velocity during a change in time. In other words, the slope of a velocity time graph. Then we noticed an interesting thing. We noticed that the slope of the xt squared graph was about half of the value of the slope of the vt graph. So if we define the slope of the vt graph as the acceleration, then the slope of the xt squared graph would be 1/2 of the acceleration. Then we decided to write an equation for the xt squared graph. Since the slope of that is 1/2 of the acceleration, then our equation becomes x equals 1/2 a times t squared, where that whole expression is just rewriting the general equation for a line, y equals mx. We can apply that expression, x equals 1/2 at squared, to be equivalent to the area under our velocity time graph. So, in its fullest form, we write the area is equal to the displacement, delta x, which is equivalent to 1/2 a times delta t squared. We also reminded ourselves that depending on the shape of the vt graph, there are lots of other ways to find the displacement. If the graph is a flat line, the area is a rectangle, and we can use the relationship base times height to find the displacement of the object. If the object is uniformly accelerating so that the graph looks like a triangle, as in the middle, we can use our old friend area equals 1/2 base times height to find the displacement of that. And bless your heart, if you remember the formula for the area of a trapezoid, you can also handle graphs like the one on the right. Inquisitive students may ask, what would we do if we wanted to find the displacement if the vt graph is curved? And there is a way to do this, but it requires use of the calculus, which you'll have to wait for later in life. If later on you enroll in AP Physics C, you will deal with this to your heart's content. In our course, we'll be working only with uniform acceleration conditions, and that means we'll only be working in situations where the velocity graph is either flat or a straight diagonal. But that would include a situation like this, where you have an object with a non-zero initial velocity, then accelerating at a constant rate for a certain amount of time. How would you find the displacement here? Well, one way to do it is to see this graph as consisting of two shapes. One of them is a rectangle having height v sub 0 and base of t. And the other one is a triangle on top of that. So if you know the final velocity of the object, you can find the displacement of the triangle using 1/2 base times height. We can also do this algebraically in a different way. We can say that the area of that rectangle is v0 times delta t. And we also found out before that the area of that triangle would be 1/2 a times delta t squared. So in a case where we have non-zero initial velocity and uniform acceleration, we can find the displacement of the object using the relationship delta x equals v0 times delta t plus 1/2 a times delta t squared. That equation might look scary, but with some study and some practice, that'll be just fine. If you're looking for other things to be scared by, I present the following costume ideas. I think if you came out of the shadows and surprised the neighborhood trick-or-treaters, they'd never come to your house again. Wouldn't want to meet this fellow on a darkened street either. You can learn more about the physics of zombies if you take my AP class. Most people don't know that Batman had a younger brother named Steak Boy. Ouch. Sometimes when you dress up, you even scare yourself. If you have a grandmother of a certain age, you might be able to dress up like the Queen. Yours truly, with the guidance lady, dressed up as Willy Wonka and the Oompa Loompas. And if you have younger siblings at home, don't forget them. Clearly adorable and tasty. Thanks for watching. See you next class.